The learning goals for today's lecture will be the use of units, fundamental quantities, base and derived units, powers of 10, conversion of units, consistency of units, and significant figures. Use of units. The units is expressing the numerical value of any physical quantities. So, for example, the physical quantities of distance and length can be expressed in unit of meter, feet, miles, or kilometers, while the physical quantities of time can be expressed in units of seconds, hours, days, and years. Sometimes we need more than one unit to express the physical quantities. So, for example, the speed, which is by definition equal to the distance divided by time. So the units of speed will be the unit of distance divided by the unit of time, like miles per hour, kilometers per hour, meters per second. All physical quantities can be defined in terms of a very small number of fundamental physical quantities. The three fundamental physical quantities are the length, time, and mass. The length of an object is defined by comparing the object with a multiple sum of standard length, such as a meter. The time of any event is defined by the measurement of event's time on a clock and using a standard units of time. And these units are hours, minutes, or seconds. While the mass can be measured in units of kilograms or grams. Base and derived units. So base units are the units used to express the fundamental quantities. For example, meters, feet, seconds, and hours are all base units, since they are used to measure two fundamental quantities, length and time. Derived units are the units used to express all other quantities. For example, miles per hour or meters per second are an example of derived units. Base units are further characterized as being either primary or secondary base units. So for each fundamental quantities, one base unit is specified the primary units, and all other units for that quantities are secondary. For measuring time, for example, the second is a primary based unit, and minutes, hours, days, and so on are all secondary based units. Powers of 10. Units that are powers of 10, multiples of other units, are often used for convenience. And so we use certain prefixes that denote the multiples. So for example, the 10 to the negative second, we can use a prefix of centi, and for the 10 to the negative third, we can use the prefix milli, and for 10th to the power third, we can use the prefix kilo. So an example, for the length measurement, 1 centimeter is equal 10 to the negative second of the meter, 1 millimeter is equal 10 to the negative third of the meter, and 1 kilometer is 10 to the third meter, and so on. So in this course, we'll see more common powers of tens, measurement units. Conversion of units. It's often necessary to convert units from one system to another. For example, you may need to convert a distance given in miles to units of meters. So to do this, you can use the conversion factor. 1 mile equals 1,609 meters. Another example, you may need to convert a time given in days to the units of seconds. So 1 day equals 24 hours, and each hour had a 60 minute, and each minute had a 60 second. So if we take a unit of days and unit of hour and unit of minute and multiply 24 times 60 times 60 seconds will equal consistency of units. The units are carried along in calculations and treated as algebraic quantities. So we then obtain from the calculation both numerical answer and the correct units. Using the units in this way will alert you when you make certain common error. So for example, if we have this rectangular shape and you asked to find the area, let's assume that the length of this shape is 2 meters and the width of this rectangle rectangular shape is 180 cm. So the area equal the length times the width. This is length, this is the width. So the area equal 2 meters times, we need to make the consistent units. So this units in centimeters, this unit in meters. We need to convert the centimeters to meters. So 1.8 meter. In this way, the area will be 3.6 meters squared. Significant figures. Physics is an experimental science. That means physics science is always dependent on the measurements. And when we do a measure of physical quantities, there's always some uncertainty in these measurements. So for example, if we want to measure a dimension of a disk, this disk, using a meter stick, and this meter stick has the smallest divisions of millimeters. That means the smallest part in this stick is millimeters. Your measurement may be accurate to the nearest millimeter. So if the length of the disk is 98.6 centimeters and there is 1 millimeter of uncertainty, that means you believe that the length of the disk it will be between 98.5 centimeters and 98.7 centimeters. Significant figures or significant digits are important to make a systematic flow of a big calculations and avoiding error propagation. So in our experiment, sometimes we need to do a multiple calculation through a multiple devices, and each one of these devices has its kind of accuracy. So to avoid the error propagation through our calculation, we need to follow some basic rules. And these basic rules, we call it the basic rules of significant figures. Number 1, all non-zero digits are significant. Number 2, the zeros between non-zero digits are significant. Like, for example, 705. So we have 705. We have a zero between two non-significant figures. So now the zero is a significant. So in this way we have a 3 significant figure in this number. And another example, 80,008. We have a 3 zeros between two non-significant figures. So these zeros are significant. So on this number we have a 5 significant figures. Number 3, leading zeros are never significant, like 0.03. So there is 2 leading zeros in this number, and these zeros are not significant. So we have only one significant figure in this number, which is number 3. And in this number also, we have 0068. So these 2 zeros are not significant figures. So we have only 2 significant figures, which is 68. Trailing zeros are significant only if a decimal place is represented. So for example, the number 100 doesn't have any decimal places. So these zeros are not significant. So the number 100 has only one significant digits, which is number 1. And 380, also the zero, and also this number doesn't have any decimal places. So the only 38 at the beginning is 3 and 8, sorry, as the significant digits. So we have a 2 significant digits. But in this number, when we say 38.00 and we have a decimal point in this number, so these zeros are a significant figure. So this number now has 4 significant figures. The same thing for the 590.0. We have these 2 zeros in this number. And since there's a decimal point in this number, we have 4 significant digits in this number. The same thing for these numbers also. We have 1, 2, 3, 4, 5, 6 significant digits. When 2 or more numbers are multiplied or divided, the final answer should be given to the number of significant figures equal to the smallest number of significant figure in any of numbers used in calculations. So for example, if we multiply 15.025 times 20.1, and the answer will be 302. So the first number, the 15.025, has 5 significant digits, and the second number, the 20.1, has 3 significant digits. So the answer should be in the 3 significant digits. Same thing, if we divide 1.35 divided by 0.24, so this number has 3 significant digits, while this number has 4 significant digits. So the answer should be in 3 significant digits. So when you add or subtract numbers with different significant figures, the number of decimal places returned in the answer should be equal to the smallest number of decimal places in any of the quantities you added or subtracted. So for example, if we have this number of 12.25 has 4 significant digits with 2 decimal places, and this number 0.6 has 1 significant figure with 1 decimal places, and this number 44 has 2 significant but there's no decimal places in this number. So the answer should be without any decimal places in this number. The 57.